Well, welcome back, everyone. It's glad to see folks have kind of made it through this winter storm. Any questions or comments before we get started today? Okay, well, for our work today, we're going to be finishing off section 3.6. That's going to be the last section that's going to be on our second upcoming exam. This exam goes from sections 3.1 all the way to the very end of section 3.6. And one thing I've decided to do with section 3.6 is try to make it really not a major part of the exam. There's going to be some major hints on what that problem is going to look like. And it's going to be through quiz number 7, our brand new quiz. This is something I like to do with exams. Whenever there's a section that we're just finishing off and we're going into, I usually try to write down a question on a quiz that's pretty similar to an actual real exam question. And that's my way to make it kind of more of a fair setup. So if you can solve this quiz number 7, you're going to do really great on section 3.6 on the second exam. It's going to be just about like this one here. Different kinds of numbers is only difference. And another thing you can do is if you decide to solve this quiz and send it in to me early, I'll try to grade it early as well and give you feedback. That way you'll have a good understanding of where you're at on section 3.6 as it relates to the second exam. So we have let me go to this document here, second exam coming up. Just like before, it's open calculator, but this time the calculator is more of a requirement than kind of a safety net. It's going to be used primarily in section 3.6 and for wherever else we might need support for, but we'll absolutely need it for that one section over there. Exam is also closed notes, but I'm going to be providing this formula sheet right here, and here's how it goes. Because exam 2 is fundamentally just all about taking derivatives, I included the table of differentiation formulas. This is a kind of a periodic table to calculate derivatives for the things we've seen from section 3.1 to 3.6. The chain rule is also stated here in its ordinary form. And this is the section 3.6 formulas. This is the derivative and differential equation on one. And this is the solution. Usually we write this as P of t for population or M of t for mass or A of t for amount of dollars. But generically, you could just call it Y of t for overall formula. So this is the stuff that you would want to be familiar with. So you'll have it on your real exam 1. But knowing how to find information here, be familiar with what's on there is just as important. So as you go to study your second exam, not a bad idea to have this just available as you work through the problems. And just like the other exam, we have the sample exam 2 problems right here. These go from a section by section basis, just generic kind of math problems, different from the ones that we've solved in class. So you can just kind of scroll through here, take a look at some problems, solve a few, and the solutions are in the very back page down below. So this will be for just practicing for getting fluent on doing the derivatives on the second exam. If you want more problems, the version 2 is problems out of the actual textbook. So you'd go to the WebAssign, go to your course textbook, and these are primarily odd problems. You can click on those problems there to reveal the answer. And this would be another great way to review the information for the second exam. When I go to write the second exam, in fact, I have already written it. Whenever I write a problem for the exam 2, I double check a few things. It's got to be a problem that was something we did in the lecture notes, something that might have been on a quiz, something that might have been on WebAssign. And that's to me what makes a great exam 2 question. So these 2 documents here, this one and this one, are just a whole host of other problems you could solve and practice with. Well, any other questions, folks, with the upcoming exam? Okay, and my hope of hopes is we get a faster turnaround in the testing center in Pocatello. They should get the exams back, and my hope is I should have this graded before we go to spring break. But we'll see how things work out in practice. So aside from that, if you're studying for exam 2, I'd say a good order of operations to get through it is probably finish off quiz 7 right away. Send it in, either email it to me or something like that, and I can give you feedback on how correct you are. After you finish off the quiz, I'd probably go to these sections and just work on them in WebAssign. Make sure your WebAssign grade is up. I mean, you're doing 2 things. You're studying for the exam and pulling up your WebAssign grade at the same time. And same offer as before. If anything looks funny there, don't hesitate to hit the Ask My Instructor button, especially over a week like this one where exam is coming up. If you hit that button a lot, I promise you never get annoyed. I'm pretty fast at typing these things out. After you solve those problems, the quiz problem, the WebAssign problems on those sections, Then I'd probably start turning around to additional problems here to try to go and get additional practice. I wouldn't try to solve every single problem. It'd be more if you feel like you're just a little bit rusty on 3.5, you could target section 3.5 problems here and here and work on those specifically, for example. Well, any other questions, folks, before we get started with today's work? Okay, well, today's work is finish off section 3.6. If we have additional time, we'll just talk more about exam one, maybe do a couple practice problems. And I have 3.7 available here, but this is more just for a preview of what's coming next. So here's where we left off. Always kind of disorienting to do a problem across a weekend. So let's refresh ourselves on what happened on this. They told us a bacteria culture grows at a constant relative growth rate. From that statement alone, we wrote down the function that would satisfy that. The differential equation's on the left. That's the solution. If the bacterial count is 600 initially, we just plugged 600 right inside here in the formula. So we came to that stage. But then to find the value for K, that's kind of more than half the battle in this kind of thing. We had to use this additional information. A bacteria count of 75,000 at 3 hours can be rewritten as this statement. You might as well just highlight that to connect the dots. Then we took the 3, that was 3 hours. It goes in for time right here. And so we just took that, plugged it in. And these were the steps to solve for K. And once we have K, we have the whole function. We went to right here, plugged it in. And this models the growth of the population of bacteria at time t. Anyone have any questions on the work through on this one? Okay, that was the fun questions down below. Once we have this function, it tells us to find the number of cells in 2 hours, round to the nearest cell. All we're doing now is just taking P of 2. It's a calculator problem, so this is a reminder we will need a calculator. But I do give a lot of partial credit when it comes to these kinds of problems. If you have this on paper, and this is, say, a 5-point problem, you get 4.5 points for writing out this much information. Population of size 2 means go here. There'll be 600 e to the 2 times natural log 125 over 3. So all we did this time is we took 2 and plugged it in right here for time. So we do need to get a value for this for full credit on it. But again, exams are kind of tricky with this stuff. If I see this on your paper, you're getting essentially all of the partial credit. Since I'll know you know the process, any mistake would have been a calculator mistake, which I try not to emphasize as much on a real exam. But we do have to calculate it, so here's how it's going to look. This will be the calculator I use in class, since it's similar to the TI-30XA or the TI-30X2S. We just go left to right, 600. For E, on this calculator, I just type the letter E. For your calculator, you want to hit the second button and then the logarithm to pull it up. Everything here is in the exponent position, so go to your exponent, and it's 2 times, oh, that doesn't work. I need a parenthesis, 2 times natural log 125 thirds. So that's a pretty large figure. 2 hours gives us, let's see, 1,041,667 bacteria for rounding to the nearest cell. So 1, that's a big number. Let me get back to that. 041 667 cells. What any questions, folks, on throwing that into the calculator? Okay, so this thing is growing exponentially. That's a pretty surprising figure. Let's look at it from a different point of view, just to get some intuition. The function is population time at time t equals 600, so it's already off the scale. This will be a kind of a difficult one to plot. Let's see if we can fix the y-scale in a slightly better way. This goes, we'll go from -95 to, let's go 1,000,000. Okay, so now we have a slightly better scale to show this. That it's e to the power. T would go right here for just plotting the function. And note it's definitely just going skyrocketing up. It's also multiplied by a natural log, 125. I think I finally found a mistake inside here. This number just looked a little bit huge to me. And when I compare the way the function is written down versus what I put here, there is an actual typo. Anyone spot where it is? Almost invisible to me because I made the mistake personally, but it's also just not easy to find these kinds of things. The typo here was the fact that you take the natural log of 125, close the parenthesis, then divide by 3, but I didn't do it that way. I caused the growth rate to become tremendously huge, so let's fix that right here. 125, then divide by 3. And this is the value I was actually expecting, 15,000. Let's go over here, divide by 3. Curve didn't seem to change much, but it looks like it is more correct at this stage. So again, that was an honest to goodness mistake, but if this was a real exam question, this is what I'm really looking for because I'll know you know the process and silly mistakes on the calculator are pretty easy to do. So let's refine and put in 15,000 said right there. Oh, sorry, missed a chat. Yes, it was in the parentheses right there as well. My 3 should have been outside. Sorry, I missed that chat on that one, right, Shiley. So this should have been exactly 15,000 cells. We did it, folks. We built a function, and we used that function to predict a bacterial count at 2 hours. And you know, I should have known that that number was way out of line when it said a million, because they told us it was only 75,000 after 3 hours. So in 2 hours being at 15,000 seems like we're on the better track now. Well, next question is where it gets a little bit different. It's asking not for the number of cells, but it wants a so-called growth rate. And the moment you see the words like rate in a problem, this is a derivative. In other words, every derivative is a rate of change. What's changing? It's going to be the change in the bacterial count. It'll be the rate of that change with respect to time as time changes. So that's kind of tricky in a certain sense. That means there is one way you could solve this problem. If it's asking for the growth rate, you could differentiate this function right here. You would find the derivative, and then you would just plug 2 hours inside that derivative. But actually, this problem is a little bit different. Where we really started with on this problem was there. The derivative was already supplied, and we solved this differential equation to get the solution. So in other words, it's not something like this we ever have to do. If we differentiated this kind of function, we just get that result right back each and every single time. And that's what this is trying to indicate. So the next question is really a calculus question when you see this, and it means we're going to start by writing in the original differential equation, the rate of change of the population size with respect to time. Again, that's kind of a nice situation, but it's tricky if we forget about this, that the derivative was already there looking at us. But we're also evaluating it at time t equals 2 hours. So the whole thing will turn into k. So that's the k you see right here, where the green box is, times the population size at time 2 hours. So now we've got this. Notice we're pretty much done because we've calculated population at time 2. We just need to take this value for k, natural log 125 thirds, multiply it against population size 2, which was 15,000 cells. So times 15,000, and we'll get a number out. So that's all we have to do on this kind of problem. Does that make sense to folks on getting through this so far? Okay, let's crank it out to get a number. It is first natural log 125 thirds, then multiply by 15,000, and we get this figure. We're rounding this one to one decimal place. It's 24,141.6. And as far as the instructions go, we did it, folks. That's correct for full credit to the letter. It didn't ask for the units, but let's put in the units just for the sake of practice. Anyone know what the units ought to be for this one here? Any volunteers for stating them? Exactly. So the cells comes from the numerator. It's a population size in terms of cells. It's a rate, so saying per or division bar would make sense. And the denominator is with respect to time in hours. So this would be cells per hour. Oh, it would be just at the per hour, but it would be relative to the time at 2 hours. So in other words, you can imagine, just for a different analogy, if you're doing a road trip that took 5 hours, all this is saying is that the 2 hour mark, this is how fast you were going. Or for population like this one, we knew at the 2 hour mark, there's 15,000 cells, but at that specific moment in time, it's growing at that particular rate, this many cells per hour. Other questions about that so far? Okay, so that means the thing is really growing exponentially pretty quickly. And other follow-up questions we can now ask is, at what time will the population size reach 200,000? Now, this one's not the calculus question, but it's still a good one to practice solving equations like what we did over here, and just working with the model a little bit more to see what it says. But I would say this one is probably the more important question in the whole course, because you might have observed a lot of this material is kind of review in a way, college algebra review, but this is the one spot where this is the new information, or this is the new content. Well, this question is so far pretty close to what you'll see on a real quiz question. This is quiz 7. That's going to be pretty similar to the actual real exam question. The rest of the problems we're going to take a look at are just further practice along these lines. And so let's solve this one next. It says, when will, so we're solving for a time, the population reach 200,000? Because they said population right here, we should just write in P for population. We don't know the time, so we just throw it in as an unknown variable. And we want it to reach or be equal to 200,000. So we haven't done much at this stage. We just retransferred this into an actual equation. But then up here, we can make a substitution. Right where you see P of t, throw in 600, e to the power of t times natural log 125 thirds, set equal to 200,000. So I made a substitution that goes like this. For P of t, we just threw in all of that information, and it went down to that spot. Any questions, folks, to that stage with the substitution step? Okay, we're happy with that as it stands. Then the next thing to do is, well, it's pretty much the same kind of process that we did up here. The objective on this one was we were solving for the growth rate k, but it's the same kind of steps. Only difference is we're solving for time this time, as opposed to the known growth rate. So first thing we want to do is isolate the exponential function, the base c exponent. So divide both sides by 600. We'll have 200,000 divide by 600. So 33 looks like 0.3 repeating. 333 rather, 0.3 bar. So I'll just write it in that way. Left-hand side is e to the power t, natural log 125 thirds. And that gets us, well, a step closer. If we solve took a peek at what our solution was to solve for the growth rate k, the next thing you do is just take the natural log of both sides. So it'll be natural logarithm e to the power t, natural log 125 divided by 3 equals, we have to do the natural log of the right-hand side too. So natural log 333.3 bar. And this is the reason we use the natural logarithm. Right here, there's a cancellation immediately, and we freed up the exponent. We can now actually officially solve for t. So the next step, t, natural log 125 thirds, is now equal to the natural log of 333.3 bar. Almost there, folks. One step away, and we'll solve for the variable t. Any questions at all so far? Okay. All we're doing is going to be multiplying by the reciprocal of this. So multiply both sides by 3, divide by natural log 125. And t comes out this way. 3 natural log 125 times natural log 333.3 bar. And we've got it, folks. That's the time at which the population should reach 200,000. But we have to actually create this out. So this is our next step. Plugging it into a calculator. So let's do this one carefully, see how it goes. Just kind of move that over. It's now just more of a calculator, not a graphing tool. So first, let's put in this fraction, 3 over 1 natural log 125. Then multiply by this natural log 333.3. Now, this is a good opportunity where we should say, you have to be really careful about the numerical values of this kind of stuff. If it's an exam problem, I'm completely fine with that as an answer, because I'll look at this step. Oh no, you just rounded it to 0.3. It's not really a big deal. But it is a big deal to WebAssign. WebAssign has a high amount of precision they're expecting for their answers, especially when it's a numerical answer like this. So if it was 33.3 repeating, that might not be precise enough. Let's check. If I put in 1 extra 3, well, did it revise much? It revised in this position, the 4th decimal place. So depending on how WebAssign feels, that might be a big deal, maybe not in this problem. You might have been actually pretty safe on this one. But here's what I would recommend regardless. Put in a whole bunch of those, make it as accurate as possible, because it doesn't hurt to just hit the 3 a whole bunch of random times. And this is the more accurate answer. This one's going to be rounded to 2 decimal places. So this will be 3.61 hours. That means we did it, folks. At 3.61 hours, we're expecting the population to catapult up to 200,000 bacteria. And that might seem about right in a certain sense, because we know at the time 2 hours, it was growing at 24,141.6 cells per hour. At the time 2.1 hours, this figure gets bigger. At 2.5 hours, it's probably closer to 100,000. It keeps changing with time as well. So at a measly 3 hours, 3.5 hours, a little bit over, that seems about right for 200,000 bacteria altogether. Well, that's the full problem. Any questions or comments, folks, on running through this one? Yeah, sorry.
Clarify, so in the second to last step where the log is inverted, so to clarify, for t is log times 125 over 3. Inverted, well, is it multiplied both sides, and does that invert it, or?
Yeah, I see what you're saying. It is a kind of inversion, and the step that I didn't quite write in to show it was right over here. If you're going to get rid of that, you would typically go like this. T divided by natural log 125 over 3. But if you wrote it this way, you're going to have to write it the same on this side, and that would take an additional step. So instead of writing it this way, we've inverted it or taken the reciprocal and went like this. So on this stage, multiplied by 3 over natural log 125. We did the same multiplication on this side times 3 over natural log 125. It emerged over here. I just put that in front.
So a shortcut is basically to multiply by the conjugate on both sides. That one.
Exactly, yeah. It would be the conjugate, but the reciprocal rather. Absolutely. And the great news about the reciprocal is that natural log 125 and this one cancels off. 3's cancel off. And so we effectively just flip the fraction, multiply on this side, and you're all set. Yep, you betcha. Other questions about that solution so far? Okay, so this is what growth models typically look like. Now let's turn the gears to take a look at anything that has to do with decay. So we can do the same kind of problems as before, but for looking at exponential decay, the kind of problems we're typically looking at are ones that involve half-life. Some of the problems in the homework will give us a half-life in maybe a roundabout way, but there's another problem where we have to come up with it ourselves using maybe some extra data. So there'll be 2 more problems down below using this kind of models. And let's put this on a new page. It says here, if a quantity is decaying exponentially, then its half-life, the time it's going to take for half of your material to vanish or disintegrate, is designated by this symbol, usually lambda. Let's write that out. Any new Greek symbol we should just write out. If you see this is the Greek letter lambda to designate half-life. So that's kind of nice in a way. And notice what half-life is conflated with. There's a K value there. That's the decay rate. And so one thing you can do with this equation is you can just turn the whole thing around. This equation is great if you're trying to solve for half-life, so we might need it in the next problem. But if you want to find the decay rate, it'll be K equals negative natural log 2 divide by lambda. So the way we get this solution is you can visualize it this way. You can multiply both sides by K, it would cancel this one. Divide by both sides by lambda, it would cancel here and merge there. But another way to think about it is it's a kind of cross product where you're just interchanging K and lambda, and that's always a valid algebraic maneuver, as long as there's just one term on the left side and one term on the right-hand side. Then you can always make that step. So the formula here is the official one for half-life, but this one down below is just as good. Well, any questions, folks, about the half-life formula at the moment? Okay, if we're dealing with half-lives, then this is always a fun one to deal with. Plutonium-239. I believe this one is fissile material, so this is the kind of stuff that people want to definitely try to control. And it has a half-life of 24,110 years. So if you have 100 grams of this stuff, well, it's going to stick around for a very, very long time. By the time half of it's gone, we're all dust as well. We're told a shipment of 1,000 grams of plutonium. I don't know how much this is. That could be like a disaster level of plutonium. Who knows? But we have 1,000 grams of plutonium, that kind. It arrives at a secure location where it's going to be just stored indefinitely. Probably the right thing to do. So we want an expression for the amount of mass that remains at time t. Well, the moment they said half-life, this is an exponential decay problem. So we can write down the derivative dm dt. This time we're using m because m is going to be the mass, and it's going to be k times m. That's our differential equation, and it has an immediate solution. The solution to this is mass at time t equals the initial mass, mass at time 0, times e to the kt. So just from them saying half-life, it's an exponential decay process, and all of this stuff is suddenly just off the table by that one statement. So that's kind of nice in a way. But when it says find an expression for the amount of mass that remains at time t, we really have 2 things we have to solve for very next. We need to find the initial mass, but that was this right here. the shipment of 1,000 grams is telling us we have 1,000 grams initially. So mass at time zero is 1,000. And now we get to update the model. Mass at time t is now 1,000 times e to the power of kt. Next step, we need to solve for k. And the problem above, that's kind of a more involved process. Quiz 7 is a little bit similar as well. But in a half-life problem, it's almost essentially looking right at us. This is the value for k, so we'll write in k equals negative natural log of 2, divide by lambda. Lambda is the half-life of 24,110 years. And so that's what's going to go into the denominator here. 24,110. So we've pretty much got it to that stage. We're going to write down the whole function now. It's going to go like this. It's almost unfortunate because you can approximate this and get some high-level precision, but what we want is the exact function. K has got to go exactly right there, so mass at time t is now 1,000. E to the power, I'm going to put negative t first. So I've already used up that negative sign. Then go natural log 2. Divide by 24,110. Let me make this sign green as well to just show where it came from. You don't have to put the t right there, but if you put it out here, it just looks kind of funny, like you might be dividing by it. That's the only reason I like to throw it in that position. Well, we've got it, folks. That's the function, and we came up with it really fast this time. And now we have a couple of just fast follow-up questions to go along with it. Any questions at the moment first on producing that function? Okay, so it's asking, after 100,000 years, how much of the 1,000 grams is actually remaining here? And you know, that's not too bad in a way because 100,000 years is almost 4 half-lives. So you can almost kind of reverse engineer and get an expectation before you even do the computation. Let's do that ourselves, just because it's, a good test-taking strategy in actuality. We want to, before we even calculate, have kind of an expectation of the number we're getting. So if we started with 1,000 and 24,000 years goes by, that's a half-life. We're down to 500 grams. Double that, we're about 50,000 years, not exactly. That means just divide by 2 squared. Now, if we're adding another 24,000 years, we're about at 75,000. That's 3 half-lives, so raise it to the power 3. And to get to this, it's not quite 4 half-lives, but it's close. So we're just estimating. Put in 2 to the power 4. And we're thinking about a figure around that mark. Not exactly, it's probably going to be more because this wasn't exactly 25,000 years. But does that make sense to folks on why it should be about that much? Okay, so after 100,000 years, who knows where society is at that point? There's still a bunch of fissile material left over, but we want to know exactly how much. So let's calculate it this way. So the 100,000 years is going to go in right here for time. It's going to be mass 100,000 equals 1,000 e to the power of negative. Now for time, put in 100,000 going this way. And then the rest of this is, I'm just copying in natural log 2. Divide by 24,110. Okay, we've said this a couple times, but just another reminder. If this is on your exam, on your real exam 2, you get essentially all the partial credit, even if you made a calculator mistake on the next step. But regardless, let's try to go for accuracy, see what this comes out as. I'll leave that figure there so we can compare it. And I'm just going to type in 1,000 e to a power negative 100,000 It's a shame you can't put commas in this. It makes it a little confusing to get those numbers right. Natural log 2, and then divide by 24,110. And, oh, not sure if I got that in right. Let me see. I'm coming up with a lot more mass than I expected. I have a negative 100,000, so that's
It looks like you have 241,000, not 24,000.
awesome. Thanks for spotting that. That was completely invisible to me. So yeah, I have too many ones on there. Maybe if I zoom in, it could help me a little bit more. I might need a new prescription on these, who knows? So that was 24,110 like that. Good eye on spotting that additional one. And that's the number we're expecting. A little bit less than what was here, but that was just a back of the envelope estimate. So we have some good trust on that figure there. To the nearest tenth, it's 56.4 grams. And again, that's the thing that's kind of tricky about exam. I'm trying to punch this in on a non-stressful environment. So on a real exam, we still have to attempt to put this in, but it's a little bit lower stakes. If you make a silly mistake like I did, you might lose a half a point, nothing major. Any questions, folks, on getting the 56.4 grams? Okay, now just like before, this is the new content. Let's just put a little star on it to just emphasize that. And it's also a really confusing question. It says at what rate? So from that statement alone, that indicates what you're really doing is the rate of change of mass with respect to time. So you're just going back to the original derivative. This is the reason I'd like to state it right here, even though we were working with this function for the most part, because this will also come right back. In fact, let's just make the arrow go both directions. They're both equally important. This is the question, and that's the answer, and vice versa. And so over here, we'll just take the derivative, dm dt. It's evaluated at time equals 100,000 years. But that means we're just going to take k times m. And the m we write in as m at 100,000. So we're just about there. Any questions, folks, with this stage of the process? Okay, let me just circle this. The moment they said at what rate, this is the idea that we had to throw in down right here. And now it's just a really fast computation. As an exam question, you have options on doing this, but as a WebAssign question, if they asked you to round right here, and then there's a follow-up computation, WebAssign is coded well to understand you're probably using the rounding error, the rounded answer, and that's okay in your work. So I'll work it in by putting in negative natural log 2, 24,110, multiplied by the approximate value, 56.4. And let me put the units in the last step. Then we're back to decimals. Let's crank this one out as carefully as possible. This will go negative natural log 2, then divide by 24,110, be careful with those, times 56.4. And this is how much it's decaying at the 100,000 year mark. This is the amount per year. It's, let's see, tens, hundreds, thousands, about 16 10,000ths of a gram per year at that time. Well, any questions, folks, on getting that figure so far? Okay, let me put in negative point. This one said round to 1 decimal place. Let's maybe change the instructions on this one, because to 1 decimal place, that would just be 0, no change at all. But there is something actually changing here. Let's make a quick edit on these instructions. They're suddenly looking a little bit silly. Let's make this one be 4. Sorry for the quick edit. Usually I try to avoid those. So to 4 decimal places, lost my window. There it goes. It's negative 0.0016. The units of this would be the unit for the mass, which was grams. The unit for time, this one is in years, so grams per year. So not too much. And if you ask the same question at, say, 100,000 and 10 years, this figure would update. It'll update on every single instant of time as the model changes. But at the 100,000 year mark, this is how much is left. And it's disintegrating at that rate at that one moment in time. Any questions, folks, with that part C there? Okay, so that's the exponential decay side of the process. And again, it's not too bad because the formula right here allows you to build the function rapidly because k is usually not too hard to spot. Let's see what else we have going on here. The last question on this is, how much time must pass in order for there to be just 1 gram remaining? So just a really fast follow-up question. Mass at time t equals 1 gram. So we started with 1,000 grams, and we know after 100,000 years, there's still 54 or 56.4 grams. So we're expecting a really long time range on this. I'm not really sure how long. And the decay rate is even a worse side of this picture. That decay rate becomes smaller and smaller and smaller as time gets larger and larger as well. So this could be a very, very long time to get just to 1 gram. The way we find it is right here at mass at time t, plug in the function we built. It'll be 1,000 e to the negative t, natural log 2, divide by 24,110, is set equal to 1. Then first thing we'll do is divide both sides by 1,000, maintaining that familiar process. We'll also hide that problem down below. So e to the power, negative t, natural log 2, divide by 24,110 is 1 over 1,000. So, or you could say 10 to the power negative 3 if you prefer. I'll leave it in that format. Next step we take is just the natural log of both sides. It's a lot of writing to write in this middle step. So if you get comfortable with skipping this step, it's actually not a bad one. Let's write it in just to show what it looks like in the notes. Natural log of all of that, negative t. Natural log 2 divided by 24,110 equals natural log of 1 divided by 1,000. Then we always anticipate this cancellation. And so it's a foregone conclusion that you are going from this line right here down to this line. Negative t, natural log 2, divide by 24,110 equals natural log 1,000. So again, if you're comfortable with doing this step, this is an okay shortcut to take. Because again, in these models, you'll notice we do that all the time. There's an expectation you're taking the logarithm somewhere. So this is an okay shortcut. In an exam setting, its value is that it saves a lot of additional writing right here on this stage. Then finally, once we get here, we'll use the same kind of idea. T is immediately solved by multiplying by the reciprocal of all of this stuff, including the negative sign. So it'll be negative 24,110 divided by natural log 2 times natural log of 1 divided by 1,000. And because we have an expectation about this time value, we know that this had better be in terms of hundreds of thousands of years. But before we get too far, let's come down right here and pause at this stage. Does that make sense to folks on how we got to that line? Okay, if we feel good about it, let's throw it back into the calculator. And here's how it comes together. Negative 24,110 divide by natural log 2. Now that looks concerning because it looks like we have negative time, right? But we're actually okay because this function is negative as long as the input is less than 1. So we're multiplying by a negative number the moment we go times natural log 1 divided by 1,000. And it wasn't as extreme of a time range that I was expecting. I was thinking it'd be closer to 1,000,000 years, but that seems about right. 100,000 years took us to about 56 grams. So 240,275 years takes us to 1 gram finally. For the rounding, they want the nearest tenth. Honestly, if this was an exam question and you just ignored the rounding, that's okay with me because that's a long time range. We're all pretty much dust at that point. 240,275.1 years. So in other words, if you have 1,000 grams of this isotope of plutonium, it's sticking around for quite a while. I don't know of a good way to dispose of that kind of stuff. Any questions, folks, on getting to that conclusion? Oh, sorry about that. Okay, so these are kind of the major problems that could have come on exam 2. But because we lost a day, the reminder about exam 2 is that this problem, or this section 3.6, is going to be a problem highly similar to quiz 7, which is very similar to example 2 on these notes right here. So what we're doing right here is mainly helping for the homework and getting additional practice as well. With that in mind, the purpose of example 4 is there's one just like it on WebAssign. In my opinion, this is the tricky one. And so this is a good one to come back for WebAssign. Let's put here similar to, I think it's the last exercise. So I'll put similar to the last WebAssign exercise. So all we know is we're dealing with tritium-3. We know it decayed to 94.5% of its original amount after a year. So you can imagine that this is something that scientists had to do back in the day when they're looking at brand new isotopes, when they're looking at new elements. If they come up with something new in the periodic table, something crazy over there, I don't know if you can see it if you're on Zoom, they have to verify these kinds of things. And, well, they might just observe the mass after a year and get a data point. That's what this is representing. There was only 94.5% of its original mass after 1 year, but we don't even know what the original mass is on this problem, and yet we're supposed to come up with the half-life some way, somehow. That's kind of a weird problem, but here's how we can get at it. Probably a little bit of space to start. Now they told us something is decaying, so it looks like we're dealing with an exponential decay problem. We can write down the standard kind of things. The differential equation is that the derivative of mass with respect to time is the decay rate, k, times mass. But that's equivalent to the function. This is the solution to the equation. Mass at time t equals initial mass. I'm going to write it down this way, m naught, or m sub 0. Because this time I don't actually have any function notation to indicate what its value would be. That's multiplied by e to the kt. Just for the sake of tying together our thoughts, let's just say what this is. M naught is the initial mass of tritium-3. So that's all we have so far, and somehow we're supposed to come up with half-life on this thing. Well, one thing we do know is that half-life, indicated as lambda, is negative natural log 2 divided by k. So sometimes when you're doing a problem, this is a decent kind of problem-solving strategy. Write down on the paper what you're going after, and it kind of could lead you to the next thing you should calculate. This is the half-life, and we'll calculate the moment we come up with k. So all of our efforts now is solve for that K value. Well, any questions or comments at the moment, folks, with the process? Okay, well, to solve for the K value, there's still one piece of information we haven't used. They told us we had it decay to 95% of its original amount after a year. And when they said original amount, they're referring to the initial mass. So this is a really, really loaded statement out of nowhere. So let's dissect this and write down an equation. It's talking about the amount of mass at time t. If it's decayed down to this figure, 94.5%, then we can convert that to a decimal, 0.945. It's 94.5% of the original amount, which is referring to m naught. To me, this is the key to the problem, but it's a weird kind of solution. I wouldn't necessarily guess that I need to write down m naught, think of it in this terms, and that information reconvenes in this kind of equation. To me, that's kind of surprising and not my first thought with these problems. But does it make sense on how it gets to that point? Awesome, I'm glad to hear that. If we're happy with this stage, then it's pretty much the same kind of operations we've been taking all along. To solve for K, we substitute mass at time t with all of that stuff right there. So it'll become m naught e to the kt and not quite. I missed one little thing when I wrote all that in. This said after a year, so that's also a function value that we're throwing in. We should have put right in this position a 1. That was something I missed on this. Again, that was a really, really loaded statement. There's 3 things going on there. The percentage, the original amount, and the fact this happens at time is 1. Let's make that pop a little bit more, since that is, I mean, that was tricky for me. Let's put in a year here means there had to be 1 in this position. It goes in for time, so it's times 1 right here as well. That means it's just going to be a K, but we should know where all that stuff goes, or else this could be a confusing question if it said 2 years, right? We have to know where everything actually gets inputted in. Then it's equal to 0.945 times m naught. Now, this is the surprise about the problem. At first, it seems like it's not quite right, but this is true. You never actually needed to know how much mass there was initially. If you're looking for a half-life, the next thing you would do is divide both sides by m naught. Here and here. And so that initial mass is just completely removed for the whole problem. Again, that's kind of weird, but when you think about it, tritium-3 is going to decay at its own half-life. It doesn't matter how much you have, the decay rate is always constant. That's why the initial mass actually wasn't even relevant to this problem. It legitimately just completely cancels out. So it's gone from here and here. All that's left is e to the power of k, 0.945. So we take the natural log of both sides. Natural log of e to the k equals natural log of 0.945. And I forgot to color code the k. We'll just slap it with a highlighter. Here's the next cancellation. Logarithm and base c as an exponential are just gone. And we have k equals the natural logarithm of 0.945. So there is a shortcut to this whole process. Think of this as the derivation or the explanation of how it got there. But the shortcut, if you recognize this as a legitimate pattern, is that this figure just goes right here and you have your k value. Kind of nice in a way. You're welcome to use that shortcut if you like, but there is some value in knowing how to do it from scratch like this. That's the hard way. Any questions, folks, with the shortcut or the hard way to go through it, like we mentioned? Okay, despite everything we've done so far, we still haven't actually solved the problem. It asked for what the half-life is. So our end answer down below is going to be this. Just to be specific, because it's a pretty loaded question with lots of things built into it, let's say the half-life is lambda equals negative natural log 2 divided by k, which was the natural log of 0.945. So just substitute in the value of k, we've got the exact expression. We want to round this one to 2 decimal places just to get a feel for it, feel for the magnitude of this half-life. So here's our next computation. This will be negative natural log 2 divided by natural log 0.945. So it looks like this one is about 12.25 years. How's that look to folks? Is that working out at the moment? Okay, so if we lost 5.5% of its initial mass after a year, that signifies the half-life was 12.25 years. That's kind of nice in a way. This is a pretty fast process when you connect these dots right here. This is the whole entire punchline. Kind of strange in a way, but everything else we wrote is the explanation of how we get there. If we just did this at the start, it's not very clear how we're even getting that as a legitimate answer any longer. But now that we've done all that, here's the follow-up question. If it took 1 year to decay to 94.5% of its original amount, we want to know how long will it take to decay to 20% of its original amount, meaning 80% of it has disintegrated. Let's make that our next step. To get through this one, though, we need to go up here where the function was and update it. It's now mass at time t equals the initial mass e to the power of this value k, which is down below right here, times t. Lost my place on that. So it'll be t times natural log 0.945. So that's the function. It doesn't address the question, but we've at least updated the original function. And let me see if I can get to the next spot here. There we go. I think we're going to need a new page on this one, so let's also drop it down. So they're asking, how long will it take to decay to 20%? That we can write down as an equation that goes like this. Mass at time t equals decay to 20% of its original value would be 0.20 times m naught. That's the original amount. Also value right here. So again, we're going to make a substitution, and this might feel kind of almost like deja vu at the moment, but that's the next step, where you see m of t, write in all of this stuff right here. There'll be m naught, the starting mass, e to the power of t times natural log 0.945. Equals, now I'm just copying in the right-hand side, 0.20 times m naught. Like before, there's an immediate cancellation. You're just going to want to divide both sides by the initial mass m naught, or you could just cancel it right here and now. That's just gone algebraically. Next step you would take is the natural logarithm of both sides. We've mentioned there's a shortcut to this, and let me show you what it would look like if you did it on the notes. It's a foregone conclusion you're using the natural log right here. It would free up t natural log 0.945. That's taking the natural log of the left-hand side, canceling e. You just have to recall to take the natural log of the right-hand side. 0.20 like that. What you get here, you're in good shape, but this is taking a shortcut. Does that make sense to folks? Taking that shortcut there? Okay, looks like people are okay with it. Again, the missing step is I went like this, natural log on that side, and natural log on this side to get to that next step. Then last thing to do is divide both sides by natural log 0.945. So t equals natural log 0.20 divided by natural log 0.945. And finally, we're going to get a figure. Now the half-life was, let's see here, 12.25 years. We're not expecting anything major. If I get like 100,000 years, we're way, way off of the right ballpark on this one. Let's see how good the algebra was by starting with natural log 0.20, natural log 0.945, and yeah, that's about what I expect. We're rounding to one decimal place on this one, so about 28.9 years. So it doesn't matter how much tritium you have of that isotope, it's going to take you this much, about 30 years, until you have just a fifth of it left. Kind of curious in a way, but 30 years is a long time too, so I probably wouldn't be too worried about it. Any questions, folks, on the conclusion here? Okay, well, we did it, folks. This is the last of the material that is relative to the second exam. What I indicated before was we might go to section 3.7, but that's a bad one to open up in just 13 minutes and some change. So how about an exam review question from section 3.1? Does that sound all right to folks? Okay, let me double check that. 3.1 is derivatives and rate of change. You know, the one I was thinking about in 3.1 would be about like this. It's calculating a derivative. But the one I think I'm really going to ask on the exam is going to be more similar to a 3.2 question. This one was also a quiz. And if you didn't do the quiz by using the definition of the derivative, you're welcome to redo that quiz. I'll accept it for full credit. And it's a good way to practice for the exam too as well. So this is going to be a real problem on the second exam. I'll change the function. But to get credit, we have to use this definition of the derivative. This is not actually on the notes. This is something that we have to memorize. And it's kind of like the formula for continuity. So let's take this. Maybe go about right there. And I'll throw it just below on the same notes for section 3.6 if you want to come back and check out the work here. Let's call this exam 2 review question. And let's take off where it says example 4. Let's give our own function. Let's let it be f of x equals negative 2x squared minus 5x plus 10. So it's not going to be anything too major. It's not going to be like the fractions or things with square roots. I'm probably just going to give you a polynomial function like this one, because this problem is more about understanding what we mean when we say definition of the derivative. It means we're calculating it this way. The good news, though, is that on our real exam 2, you pretty much know the answer, right? We have tools that tell us the derivative is this. Use the power rule. This will be negative 4x. This will turn into a negative 5. So that's going to be our answer. But the credit is from actually using the definition of the derivative. We just happen to know where we're going for. And so here's how this problem is expected to go. We'll say f prime of x is the limit as h goes to 0 of, I'll start color coding these so we can work them out in the margin, f of x plus h minus f of x, all of which is divided by h. So let me just put down, this is equal to limit, h goes to 0. I'm just going to leave this blank for the moment. And we'll start by working out f of x plus h. This alone is pretty good algebra review because we have to deal with function composition when we do f of x plus h. X plus h will go to that position and to that position. But you know, another way to write this out is in the same kind of strategy that we've been indicating product rule, quotient rule, chain rule. just write down the skeleton of that thing. Then after you have all that in, grab your inner function x plus h and input it into the blanks. Now we have to still do a lot of work expanding all this out, but that's a good start. Right over here, we'll write this as -2. And when you FOIL out x plus h squared, let's do this one in the margin. Recall it has to go like this, x plus h times x plus h. We'll get an x squared plus xh plus xh plus h squared each time you FOIL that out entirely. But that means the process really can go like this. Back over here, you square x to get x squared. You have xh twice, so it's 2xh. Then you square your h for an h squared. And then the rest I'm just copying in. Barely made it inside there. That look all right to folks on this step of the algebra? Okay, last thing is distribute the -2 through, the -5 through, and we get -2x squared minus 4xh minus 2h squared. Next distribution is -5x minus 5h plus 10. So that's a lot of stuff so far. But if this was, say, an 8-point exam question, I would give partial credit for just this much. I would give a lot of partial credit because you've already told me you know the definition of the derivative is this. The rest of the partial credit is just correctly executing the rest of the algebra. So all this stuff goes in. -2x squared minus 4xh minus 2h squared minus 5x minus 5h plus 10. So there it all is. And negative f of x is the freebie. That's just distributing a negative through all of this to get plus 2x squared, flipping that sign. Flip the next sign for a plus 5x, and then a minus 10. If you got to here, you're essentially getting most of the credit for this kind of problem. The rest is just finishing off the limit at this stage. We have a bunch of cancellations we're expecting. Anything that did not involve h must cancel as long as we're on the right track. If I can't cancel out that -2x squared, it just means I made a mistake somewhere. It would probably be somewhere in there is where I would guess. So this and this cancels, we're on the right track. All the way over to here, we have a -5x with a positive 5x. And off to here, it's positive 10 with a negative 10. And now we're just doing a ordinary limit. Let me circle these because I have a habit of not carrying down everything that survived. So those are the 3 survivors. We'll have limit as h goes to 0. And for the things I circled, let's also factor out an h. That means by the red dot, that's a -4x. Over here, that'll be minus 2h. And over here, that'll turn into a -5. All that's divided by h. And the factoring is just to make it a little bit cleaner when we do this next cancellation. We now have h divided by h. There's no pluses or minuses, so that's a true cancellation at that stage. And now, because this is an exam question, you'd probably finish the limit right here. I mean, that's almost encouraged at this point. H is going to 0 in the limit, and that only influences that term. I usually convey it this way. This one wasn't a cancellation. This one went to 0 in the limit, so I usually put an arrow to indicate that. All that's left is -4x minus 5. And you wouldn't have to say anything further because following the equality, you've already said that's the derivative right there. So this question is all about knowing that's the definition of the derivative and understanding how to move through the process. If you got tied up somewhere here in algebra, I'm not as worried about that. You might lose 1 or 2 points, potentially 3, but that would be on the higher end. And out of an 8-point problem, you're getting a lot of credit just by knowing that that is the definition. Well, that's my whole spiel on that exam question. And it's a tricky one because ordinarily in a calculus class, if you're told to calculate something, I typically don't care what the method is, as long as your process is correct. But there are odd times where the question is about knowing one particular method. And I'll always try to indicate that you very strongly in a real exam. One thing I did notice is I can't print out as many colors or highlighted things on real exams. They don't print out well in Pocatello testing centers and the other testing centers. But I will make it bold, so italics and stuff like that is what you can expect for emphasis. Well, any last questions or comments, folks, on this one here? Okay, I think at this point I definitely have ran out of material. So this will be our stopping point for today. And if over the weekend you're studying for the second exam, please don't hesitate to write to me over email and stuff like that, or hit the Ask My Teacher button. I'll be very happy to help out. If you decide to finish quiz 7 early, my objective is to grade it early and return it to you before you come in for the exam on Monday night. Well, have a great night, folks. Drive safe, and I'll see you all next week. One more week and it's spring break.
I'm sorry, I actually have a question on the review. Could we do 29B and H, please?
Which problem set was it?
Just the first sample exam problems.
Gotcha. Let's take a look at that. And you said, I think it was 29, right?
B and H.
Gotcha. Thank you, sir. So 29 here, and let's take a look. Oh, these are good ones. I think I saw stuff like this pretty similar in WebAssign as well. So B and H is even worse, so good call on that one. So to go through B to me looks like we're dealing with a product rule, but on closer inspection, it's also a chain rule because of that negative kx. So I would organize this one as y prime equals x prime e negative kx plus x e negative kx prime. So that would be my setup to get started on it. Does that make sense to that stage?
Yep.
Awesome. So next thing we'll do is, well, we can run through the whole derivative, but to me, the hardest part about part B is that right there. So we might as well just calculate that and see what it comes out as. E negative kx prime. This one's a chain rule, but it's tricky because it's an exponential function. So let's start by organizing it. The inner function is this. That's what's been thrown inside e to the x. Because the inner function, that means it's the derivative we'll do second. The outer function is the e to the x. Again, this one is kind of hard to really pick out that that's an actual outer function. It's outer because it's an e to the x really. And the only thing that was changed was that x turned into a negative kx. So with that initial setup there, we can say that this is going to be equal to, first do the derivative of the outer function. We'll get e to the, not quite x, we just leave a placeholder where x would have been. Then we multiply by the derivative of the inner function. The inner function is negative kx, and it goes into both of those blank parentheses. So here and here. Does that make sense on that chain rule analysis to that stage? Awesome. So this one's tough because it's a product rule, but then in the product rule, there's a chain rule. But then in the chain rule, this is not easy either. Do you see what that derivative will turn into where the red dot is?
Is it just negative k?
Good call. That one is just a negative k. It throws people off because we expect like a negative 5x or a negative 12x, but the derivative works exactly the same. You just get a negative k. So that whole thing turns into negative k, e negative kx. And that means y prime is finally can be ran through as Up here, well, that just turns into a 1, so we just copy in e negative kx. Over here, we have an x, but we also have a negative k, so I'm going to write it as negative kx, e negative kx. And so that should be our answer on that one there. Does that make sense on getting through this one?
Yeah.
Awesome. Again, these ones are pretty touchy, I'd say, part B and part H, because of that exponential function. But just to leave a paper trail, if folks would like to come back to this one, I'm going to put it under the same section of notes. So,
Sounds
wow, that looks crazy. Let me clear this off as well. It'll just be below here. No, I might as well have done that in the first place. Let me go back to this one and let's grab H next. This one has, again, a lot of issues. So you picked out some pretty tricky looking problems, I would say, on this set. The first issue with this is that's an exponential function, and we need a whole new formula for differentiating this one. This formula comes from section 3.5, and it reads like this. The derivative with respect to x of b to the power of x is b to the power of x times the natural logarithm of b. So the base right here is the major thing we have to look at whenever we're dealing with this kind of derivative, because it comes out again in this spot, and then again in that spot. So in our problem for f of x, the base we're using is 5, and if it was like this problem, y equals 5 to the x, that'd be terrific. It'd be pretty much done by saying y prime is 5 to the x, natural log 5. We wouldn't have to say anything further, but this one turns into a chain rule, so we do have to do a little bit extra on this one. But before we go through the whole process, does that make sense with the formula and the quick example below?
Yeah.
Okay, great. So next thing, let's think of this one as the inner function. It's inner to 5 to the power of x because instead of x, we threw inside root x into that position. But this function is the outer function, 5 to the x. So if when we go to differentiate this one, it looks pretty weird to start out. I can't sugarcoat it because we're using this process right here. So we go in order. 1 here means we do that derivative first. And this one as a derivative is 5 to a power, but we'll leave it blank, multiplied by natural log of 5, because that's the base. That's this part right here when we say natural log of the base. Then we multiply by the derivative of something because it's also a chain rule at the same time. After we do that, notice there's only 2 blanks here. If this was a 6, we'd have written 6 to a power, natural log 6, but we keep it as a 5 to match the base. And root x goes here and here as well. Because we're differentiating this one, it might not be a bad idea to write it as x to a half power, but there's a lot of different ways to do that derivative. If you decide to leave it as square root x, then we also wrote down this formula. I think this one was in section 3.5 as well, where derivative with root x, or excuse me, derivative with respect to x of root x, each time you do this process of writing the power to a half, pulling the power down, subtracting 1, you always, each and every time, get 1 over 2 root x. It's just a foregone conclusion. And so back over here, the derivative can be finalized by saying it's 5 to root x, natural log 5. That derivative is going to turn into 2 root x going down into the denominator, and that would be the full answer on this one right here. Well, there's lots of different ways to format the answer, but does that make sense on that format there?
Yeah. Thank you so much.
You bet. Those are definitely the trickier kind of questions. And I would say when you're looking at these, the purpose of these questions are not that they're all necessarily great exam questions, but they are the right questions to practice to be prepared for the real exam. Our real exams typically are a little bit nicer than these things.
Okay,
Well, any other
perfect.
questions, folks? Okay, well, have a great night, and I'll see you folks on Monday's class.
Yeah.
Thanks for staying overtime with me. You definitely didn't have to, though. I hear you. Yeah, when I was learning calculus for the first time, the chain rule was always something that I had to just keep staring at it, keep practicing till it finally started to click. It's a little bit weird.
I get the general concept for some reason, though.
Mhm.
It takes me a while for the numbers to come correctly.
I hear you. Yeah. For me, a lot of this stuff, it was more like, and this is not the best thing to say, but it was like muscle memory. I knew if I did like 100 problems, it would click, and it did eventually.
That's similar to my method, because
Yeah.
eventually after 100, you usually understand. If not, that's
Yeah, yeah.
then I go back to the drawing board, figure out what is not clicking.
Yeah, exactly. I mean, that's not the most encouraging thing to say, but it's the reality with math. It just lots of practice is what it takes.
Math and chemistry and probably physics. I haven't taken physics yet, though.
Yeah, I stayed away from chemistry. That stuff is too scary for me. They allowed me to get a degree without even taking one class, so I felt lucky.
Have an excellent day.
Thanks, you too.
Have an excellent weekend.
Thanks, you as well.